Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are beginning a deep dive into a really high-scoring section of Unit 9, Ray Optics and Optical Instruments. We'll be focusing specifically on the reflection of light by spherical mirrors, and I promise you a simple exam-safe explanation that will make these concepts stick for good. Okay, so let's just jump right in. Let's unpack this. When you look at yourself in a normal flat bathroom mirror, your reflection looks exactly the same size. But why is it that when you look at a side view mirror in a car,
Right.
the vehicles behind you suddenly look so much smaller
Yeah.
and further away?
Yes, that's so true. And it's the same with, say, a shaving mirror. When I get really close, my face is magnified and upright, but if I move back even a little, the image just flips upside down and shrinks. It's very confusing.
Exactly. That is the core puzzle. It's all about why these simple curved surfaces do such, well, drastically different things to light. And here's where it gets really interesting. Those huge telescope mirrors, like the Hubble, they use giant curved surfaces to focus light from galaxies billions of light years away, and they operate on the exact same principles.
Wait, really? So the physics behind a small shaving mirror is the same geometry that helps us see the edge of the universe?
Precisely. It's all based on understanding how light reflects off a curve, and we need ray optics to predict it. So the core idea, the absolute basic concept is this. A spherical mirror is just a curved mirror. It's shaped like a small piece of a huge hollow sphere. The key physical principle is that the fundamental law of reflection.
Angle of incidence equals angle of reflection.
Yes, that simple law holds true at every single point on that curved surface. But because the surface is constantly curving, the overall effect is dramatic.
So the curve is always changing the angle of the normal, and that forces the light to bend, even though the law itself is constant at each tiny spot?
You've got it. That's the key. And we have two main types. The concave mirror, which curves inward like a cave, and the convex mirror, which curves outward like the surface of a ball. For a really strong mental image, think of light rays as rain falling in parallel streams.
Okay.
A concave mirror is like a curved funnel. Each drop of rain hits the surface, but the inward curve directs every single drop towards the center drain. They all converge.
They meet at a single point.
They meet at a single point. That's why we call them converging mirrors. Now, a convex mirror is like the outside of that same funnel.
Ah, so the rain would just bounce off and scatter everywhere.
It would scatter in all directions. They're diverging mirrors. The rays spread out and will never actually meet in front of the mirror.
There's still a focal point, right?
There is, but it's different. If you trace those scattered rays backward, they appear to come from a single point behind the mirror. This difference, actual convergence creating a real focus versus apparent divergence from a virtual focus, is absolutely critical for image formation. Now, let's see how NSERT formally defines this concept and gives us the tools we need to solve the numericals. Before we go on, could you please read the formal definitions for the pole and the principal axis from the insert material?
Of course. The geometric center of a spherical mirror is called its pole,
Right.
while that of a spherical lens is called its optical center. The line joining the pole and the center of curvature of the spherical mirror is known as the principal axis.
Very good. And now for the most important part for solving problems. The Cartesian sign convention. Could you read that as well?
Yes. According to this convention, all distances are measured from the pole of the mirror.
Okay.
Distances measured in the same direction as the incident light are taken as positive, and those measured in the direction opposite to the direction of incident light are taken as negative.
And what about heights?
It says heights measured upwards are positive and downwards are negative.
Excellent. Now the key distance we need is the focal length, which is f. For the paraxial rays we use in our syllabus.
Those are the rays close to the principal axis, right?
Exactly. For those rays, NSERT shows using simple geometry that the focal length is exactly half the radius of curvature. So f equals r by 2. This means the focusing power of a mirror is fixed purely by its shape. Okay, next up are images. An image is real if the rays actually meet after reflection. You can project it on a screen.
Like in a cinema hall.
Perfect example. And an image is virtual if the rays only appear to diverge from a point behind the mirror. You can't project it. Now, all of this geometry, it boils down to one powerful algebraic relation, the mirror equation. Can you read that one for us?
Yes. The relation is known as the mirror equation. 1 upon v plus 1 upon u equals 1 upon f,
Right.
where u and v are object and image distances, respectively, and f is the focal length.
And to know the size and orientation of the image, we use linear magnification m.
Okay. Linear magnification is defined as the ratio of the height of the image h dash to the height of the object. hm equals h dash upon h equals minus v upon u.
Perfect. So if m is negative, the image is inverted, which usually means it's real. If m is positive, the image is upright, usually virtual. This one equation works for all cases as long as we use the sign convention properly. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com.second. Let's try a quick concept check example, a worked example. Suppose we have a concave mirror with a focal length of, say, 10 centimeters. An object is placed at 30 centimeters. We want to find the image location, V.
Okay, so since it's a concave mirror, the focal length f is negative, right? So f is minus 10 centimeters.
Correct. The focus is in front of the mirror against the direction of incident light. What about the object distance, U?
The object is also in front, so u must also be negative. U is minus 30 centimeters.
Perfect. Now we just use the equation. 1 upon V plus 1 upon U equals 1 upon F. So 1 upon V plus 1 upon minus 30 equals 1 upon minus 10.
Okay, so 1 upon v is equal to 1 upon 30 minus 1 upon 10.
Right.
Taking the common denominator 30, we get 1 minus 3, which is minus 2. So minus 2 upon 30.
Which simplifies 2.
Minus 1 upon 15. So v equals minus 15 centimeters.
And what does that minus sign tell us?
It means the image is formed in front of the mirror. It's a real image.
Exactly. And what about magnification? M equals minus V upon U.
So that's minus of minus 15 divided by minus 30.
Which gives us...
minus 15 upon 30, which is minus 0.5.
Good. So the negative sign for M means the image is inverted. And the 0.5 means it's half the size or diminished.
So it's a real inverted and diminished image.
Perfect. Understanding this mirror equation and sign convention is so crucial because the same principles are carried forward when we study refraction at spherical surfaces and lenses next. Now let's talk about the silent killers, those common misconceptions that cost students marks in the exam. The first one is thinking, a concave mirror always magnifies, a convex mirror always shrinks. This is simply wrong.
Oh, so I have to calculate m equals minus v upon u every single time. I can't just assume.
You cannot assume. The mirror type alone does not decide the size. The object's position, U, is what decides it.
I see.
For a concave mirror, if the object is very close, like your shaving mirror where U is less than F, it magnifies. But if it's far away, like in our example where U is greater than 2F, it shrinks.
So the rule is magnification depends on position. If I move the object, I change the magnification.
That is the hook to remember. Exactly.
Oh.
Now for the second killer. Convex mirrors can create real images, just like concave mirrors.
And that's wrong.
Absolutely wrong. Convex mirrors are diverging mirrors. Their geometry ensures they always produce virtual, upright, and diminished images. Always. It doesn't matter where you place the object.
So for a convex mirror, in my answer, I should always write virtual, upright, diminished.
That is correct. Remember, convex equals always virtual. Concave can be real or virtual, depending on position. Now, to make sure these ideas really stick, let's use a few memory anchors. Here is a simple phrase. Cave mirrors, concave, converge rays. Convex mirrors can't create real images, only view wide virtual ones.
That's clever. It connects the name to the function.
It does. And you can try a physical gesture. Cuck your hand inward. That's a concave shape. Imagine rays coming in and converging to the center of your palm. That's your focus.
Okay, I can see that.
Now flip your hand outward, making a convex shape.
Pressure.
Imagine rays bouncing off the back of your hand and spreading out. This helps you recall the basic convergence and divergence.
That's a good physical reminder.
And finally, an association. Think of the convex car mirror. It's there for safety. It gives you a wide view by shrinking everything, reminding you that convex geometry is for wide-angle, virtual, diminished images. Okay, let's quickly summarize the 3 key takeaways for this deep dive. 1. Spherical mirrors, both concave and convex, use the simple law of reflection, theta I equals theta R, applied across a curved surface to either converge or diverge light rays.
Got it.
2. All the geometry is captured by 2 simple formulas, F equals R by 2, and the mirror equation 1 upon V plus 1 upon U equals 1 upon F. But they only work if you apply the Cartesian sign convention strictly.
Right. Direction of incident light is positive.
And 3. Concave mirrors can form both real and virtual images. It depends on the object's position. But convex mirrors, they always form virtual, upright, and diminished images. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Thank you for joining us for this deep dive into spherical mirrors. Keep practicing those ray diagrams and numericals. Good luck with your studies.